Applied Physics 2, Moment of Inertia. We have a diagram as a starter here where we've got a hoop and a disc, a solid disc, both of the same mass at the top of a ramp. So the question is, which one would arrive at the bottom first if you let them both go? I'll leave you to have a think about that one. So, theory. Torque is a turning force, and it's equal to the magnitude of the force times the perpendicular distance between the axis and the line of action of the force. Equation is T equals Fd, torque equals force times distance, and the units are of course Newton meters. And that may look very familiar to you because this equation we are more familiar with saying that the moment is the force times the distance. And it's actually the same thing. Mathematicians tend to use moments and engineers tend to call them torques. So that's our first important equation. Torque is force times distance. So in this diagram here we have a flywheel, big brown thing. We've wrapped a cord or rope around the flywheel and pulling it, so you're applying a force F, and the distance to the axis is, perpendicular distance is d, so the size of the torque you're applying is force F times d. Now the next thing we need to think about is something called the moment of inertia. Everything with mass has inertia, but when you're rotating something we talk about the moment of inertia, because the inertia of a rotating body depends on its mass and how the mass is distributed. So a diagram might help here. The formula for moment of inertia is sigma mr squared, and if you look at this diagram, which looks a bit like a potato for some reason, never mind, we've got lots of masses, so M1, it's M0 I think, M5 and so on, all distributed around a centre of rotation. So if you wanted to work out the moment of inertia of this mass, you'd have to sum all the masses times their distance to the pivot squared. Units of moment of inertia are therefore kilogram meters squared. Now, how do you use that? In linear motion, we're very used to the formula F equals ma. Force is mass times acceleration. So if you're trying to accelerate something and apply a force to it, the bigger the mass, the smaller the effect, the smaller the acceleration. So it's harder to accelerate a big mass. In rotational motion, we've got an equivalent, which is T equals I alpha. So that's the torque, instead of the force, is equal to the moment of inertia, instead of the mass, times the angular acceleration, instead of the linear acceleration. So these two formulas, as you can see, are equivalent to each other. So T equals I alpha. So we've got two important equations on this screen. I, the moment of inertia, is the sum of mr squared, and T equals I alpha. Torque is moment of inertia times the angular acceleration. Now there are some standard moments of inertia that we use that crop up very frequently. For a hoop, the moment of inertia is mr squared, so the entire mass of the hoop times its radius squared. For a disc, however, the moment of inertia is only half as big. So if you want something to have a big moment of inertia and you've got a limited amount of material, it is better to make a hoop than a disc. You get twice the effective moment of inertia with a hoop. You don't have to know those formulas, but they are used a lot. A couple of others that sometimes come up, and you definitely don't have to know these ones, are that if you've got a uniform beam and you're rotating it about one end, about its middle, so about the centre point here, so imagine putting a pin through the beam here and spinning it, then the moment of inertia is ml squared over 12. If, on the other hand, you put a pin through one end and spun it there, then the moment of inertia is 4 times bigger. It's ml squared over 3. Now again, you don't need to know either of those, but they might come up in a question. They'll be given to you if they do. So finally, getting back to the question we started with, which would arrive at the bottom first? So the force that's trying to turn them is the frictional force between the surface of these two objects and the surface of the ramp. So assuming they've got the same external size, they'd be subjected to the same frictional force, so same material. If you and they're both acting, those frictional forces are both acting at the same radius from their centres. So we've got the same force, same distance, and therefore the same torque on both. So torque is moment of inertia times angular acceleration. So since the hoop has a larger moment of inertia, that means it must have a smaller angular acceleration. So the answer is that the disk would arrive at the bottom first.